Hello and welcome along once again to Enfield Physics Tutor tries to make difficult physics easy. It's everybody's favourite force, the normal force. Let's begin our discussion of the normal force by considering a simple, if rather strange example of a person standing on a table. And we'll let this person have a mass, get my pen, a mass of 100 kilograms. So they're quite a large person, but I just want to keep the numbers nice and easy. So if this person has no acceleration and no velocity, then we know that the forces must be balanced. So what forces are acting? Well, hopefully you will know straight away that there's mass times g, which of course is going to be 100 times 9.8, so 980 newtons. But at the same time, there must almost also be an upwards force to counteract that force. And that is the force that I'm going to call the normal. And we know that the force normal, or Fn, if you like, is going to be equal to the weight because there's no acceleration. So now we're going to go on to a slightly more interesting case. This time we have a person in a lift and they're accelerating upwards at 2 meters per second squared. Now, because I haven't written a minus sign before that 2, that means that we have defined upwards as being our positive direction. So downwards is negative. Now we're told that we have an overall acceleration upwards of 2 meters per second. Therefore, our resultant force here is going to be the mass of the person, 100 times 2, or 200 newtons upwards. That's the overall force. And that force can only be provided through the normal force. But that's not the size of the normal force. And the reason for that is because, of course, this person still has a weight. And the weight is downwards. And it's still 980 newtons. Although really, I want to put a minus in there because it's going downwards. It's negative, isn't it? So then we consider that we have, therefore, the normal force going upwards must be big enough to overcome this 980 by 200. So let's work out the value then of Fr, the resultant force. So it's going to be equal to the sum of the forces. So it's going to be equal to the upwards force, which in this case is the normal force, add on the weight. Now remember, we've got to take care of our signs here. So our Fn, which is what we're trying to find, is going to be equal to our 200, which is our overall force, plus minus 980. So we can effectively just scrub that out. Rearranging that, we then get the 200 plus 980 equals Fn. So the normal force created by the floor of the lift in this case is 1180 newtons. In this next example then, we're going to have the lift falling, but not free falling. We won't go there yet. So the acceleration downwards is going to be negative because it's downwards. And this time we'll say 2 meters per second squared again. And remember, positive is upwards. So if we know that there is an overall acceleration of minus 2 meters per second, we can work out the resultant force using MA, and of course mass is still 100, so it's mass times minus 2 minus 200 newtons downwards. So that's our resultant force. That's going to be the sum of all the other forces. And of course, this person here, their weight hasn't changed, still 980 newtons, which of course is downwards, and the other force that's still acting is going to be the normal reaction. Remember, this 200 up here, it's not a separate force, it's the resultant force. What happens if you add the other forces up? So we still got our force normal here. So our resultant force, our Fr, is still going to be the sum of Fn plus the weight. So let's put in the numbers. So our reaction force, our overall force is minus 200. Our normal force is what we're trying to find. For some reason I wrote an N there. That's an F, isn't it? Plus the weight, which is minus 980. Take care with the signs here. So let's do some rearranging then. So we're going to add 980 to both sides. So 980 minus 200 equals the normal force provided by the floor, which as you can see is 780. It's 780. In this last case, we will take the same person with the same mass and the same gravitational field strength. And this time we're going to somehow cut the metal cord that is holding the lift in place. In other words, now the lift just free falls. And we want to find out what happens to the normal reaction. If the lift free falls, that means that its acceleration is going to be equal to minus 9.8 meters per second squared. Remember, we said upwards was positive. So it's free falling at minus 9.8 meters per squared. Therefore, what is the net force or the resultant force acting on this person? Well, it's going to be their mass, 100 times minus 9.8, which equals minus 980 newtons. So 980 newtons downwards. And just like before, we can say that the resultant force is equal to the sum of the other forces. In other words, Fn plus mg, or the weight. Now remember, this mg technically is negative. Well, it's not technically, it is negative. And of course, it's in newtons. So let's put in the numbers then. Well, the resultant force is minus 980. Fn is what we're trying to find. Add to that mg, but remember it's negative. Ooh. When we rearrange that, we will see that the normal force from the floor, the normal force pushing upwards, is going to be 0 newtons. Now this is interesting. You experience no force upwards, and it is the normal force acting upwards through you, going upwards through your body, that you experience as weight. That's how your body knows you have a weight. So if that normal force is taken away completely, you are now what we technically call weightless, which in itself is extremely exciting and something that I'd like to experience, but maybe not in a falling lift.